what happens if we delay a policy. Oh, yeah, and also how costly it is if you want to keep dirty capital until their end of life, if we avoid or refuse to strand. So as you well know, many countries are now pledging for zero emissions in 2050. 120 is the last number that I heard. And that will create a very, will put us, if that is gonna happen, it puts us on a very emission reduction, stringent emission reduction path. And so this is a graph from the International Energy Agency. They look at coal-fired power plants. And so here we have increase in emissions from coal-fired power plants. We were building quite a few plants the last 2 decades. And so if you just stop investing, then the emissions of these plants will continue for many decades. And that's way too much emissions to be optimal in a to stay within 2 degrees. And so, for example, the International Energy Agency thinks that this orange line is what is more optimal, meaning that part of these installations have to be shut down before end of life, probably the oldest ones, the least efficient ones. Some of them can be repurposed quite cheaply. You can think of burning pellets instead of coal, but then we don't have enough pellets for all these coal-fired power plants in the world. And so there is also a more expensive retrofitting option that would be retrofitting with CCS. But what is important is that CCS on an existing plant is less advantageous. It's going to be more costly than CCS on a new build plant. And so if the coal-fired power plants weren't there, maybe we wouldn't even build any CCS coal-fired plants. So the fact that we have these existing plants is like making the abatement path more complicated and more expensive. And so this is just one example of many other physical capital stocks that we look at or that we want to represent in the model. And you can think also about of gas power plants. You can think of the networks that are there, but they are not adapted to renewables. Hydrogen steel will require quite a different type of mills. Networks, roads, they typically have a very long lifetime. And so that's the focus of our study. So we have 3 contributions compared to many other models. So first, the first point is that many models, if you think about Dietz of Nordhaus or Page or these cost-benefit analysis, they don't have any rigidities with capital accumulation. So they would jump, they can, without any penalty, jump from one level of emissions to the other. So we add these rigidities and stranding costs. Then within the literature that looks at stranding assets on a global level, often the abatement cost functions are very stylized. And so we have a data-driven emission abatement cost function. So we fit them to all the scenarios in the IPCC report and the NGFS database. And then we have a lot of uncertainties in the model, and I'll explain in the next 3 slides a bit more of detail in how we do this, these 3 contributions. So stranding costs, the mechanism, in the model is that if you abate emissions at a speed faster than 5% per year, you require repurposing of your capital, of your dirty capital. And so we assume that that is because we assume that there is a decay rate of dirty capital of 4% per year, and that even if you would not decay, there is also like even without any climate policy, there is a decrease in carbon intensity of dirty capital. But then beyond 5%, you're going to have these extra costs, and we assume that they are quadratic. So that represents this idea that if you repurpose only a bit, that it's going to be, you have these opportunities that are relatively easy. But then at some point, our star in this graph, the slope is 1. So that means you lose the entire value of your asset. That would be like closing down a plant. And then technically, you can also go beyond this point. Because then you can also think about the wider macroeconomic costs of very rapid abatement. Then abatement costs, we assume that that is relatively standard, that total abatement costs are quadratic, meaning marginal abatement costs are linear, but the slope of the marginal abatement cost becomes flatter over time due to learning, and this learning rate is also fitted to these detailed bottom-up climate energy models that are in the IPCC. I think we have 300 model scenarios and the NGFS database. Also, the cost parameter for this more expensive abatement, if it's very rapid, these rigidities in my preceding slide, they're also fitted to these data. And then we have economic uncertainty. So we have 2 capital stocks, clean and dirty. They both have Brownian motions. Then we have disasters, like in the Barrow paper. So on average, every 70 years, there is like something like a war or a very deep crisis, and you have a jump process of 20% of your GDP that is fitted to observe the data in the past. But then if the Earth gets warmer, these disasters get a bit worse. That's our representation of how climate can interact with tipping points and maybe climate. It can also be, we can also have this argument that in a warmer world, there is more likelihood of wars or things like that. We then have a Brownian motion on the temperature, so that represents gradual learning about how warm, like how the climate system reacts. This is Epstein-Zinn, relative risk aversion of 4, and so it's a recursive optimization. It's dynamic programming with 5 states, which is quite large. I know only of a very few models that have this level of complexity in this branch of optimal decision under uncertainty. So here are the results. So the yellow line is the optimal emission spot from our model with central parameters. There is also some uncertainty. So it's a Monte Carlo simulation of our optimal result. But however, the uncertainty is not done with Monte Carlo. It's recursive. So it's optimal prudence, knowing that you will adapt your plan in the future if new information arrives. 3 minutes? Natalia? I know. Sorry. Good. So if you would do the same model, run the same model, but there would not be no inertia in emissions, then the model, so like meaning in our model, no stranding or repurposing costs, then you have this purple line. So something like Dietz would start at 30, go from 55 at the start to 30 the next year, and then follow this purple line. And so adding this inertia is quite important to get the emissions right at the start. So then these are the stranding, the amount of capital that is stranded per year. And so in the first decade, you strand at the level that starts at 250 billion per year. That's what we would call a modest amount of, or a modest cost of stranding. That is the equivalent of 1% of investment. So the fact that you can't immediately stop emissions create a temperature path that has also more inertia. So we warm steeper at the start, and then in the steady state, the inertia doesn't matter. In the steady state, both models go to 2.2 degrees, something like that. And then the carbon price is also a little bit higher, 5% higher, because you need these extra costs of the repurposing. Good. Now we also compare not only we also compare cost benefit with a cost minimization to stay within 2 degrees. So it's called cost effectiveness. That is, so the cost benefit is in blue and cost effectiveness is in red. Like all the IPCC work is done with cost effectiveness, but what is not that well known is that typically if you do cost effectiveness, since you don't care about the timing of the damages, but you only care about the timing of the cost, you will postpone effort, you would push effort to the end. So the emission, there is less in this cost effectiveness, less abatement at the start, more at the end. That's a typical result. And therefore stranding is smaller. So instead of 250 billion, you're at 150. And the corollary for this, for the social cost of carbon, you're closer to a hoteling rule. The carbon price starts lower and ends higher. Now, if you want to stay within 1.5 degree with the cost effectiveness, then everything becomes more expensive. You still have this steeper carbon price path, but stranding obviously increases because the target is so high. Now, what happens if we delay action? So this is a graph. This is first for cost benefit, where we show what happens if you start later. So you would continue with business as usual, something like current emissions, and then act later. You could say that the Paris Agreement is more or less like before the new targets of these countries of zero emissions, like what is now on paper, what is now being renegotiated, is a plan where we have more or less the same emissions until 2030. So basically, then you can start in 2030 with an optimal policy, and then instead of a total quantity of stranded assets of a $500 billion, you would go to 2 trillion of stranded assets. Sorry, no, I get it wrong. This is the cost of stranded assets. The total amount of stranded assets would be 5 trillion. That is 5% of world GDP. Costs are lower than the amount of capital that is repurposed because you can recover some of the costs. It's not always 100% of the value that is lost. Now you can also do the same exercise for the 1.5 degrees. So if you start in last year, 2020, we've seen the graph, then you would have a total amount that is stranded, that is around 5 trillion. And in 2030, it will go up to 30 trillion. That is like very large. The cost would be equivalent, 30 trillion. 30 trillion, it's 30% of world GDP. It's 1 year of investment, more or less. Good. Now, what happens if you do not have learning? So if you do not have learning, you would have, you're at the red or yellow lines. Red, let's focus on red. That means you have constant marginal abatement cost, which you fit on an estimate for 2030. You use the technologies and the technology costs that you think are applied to 2030. Then your stranding is a bit more higher, because learning, if by waiting you get cheaper abatement opportunities, that's an incentive to wait. And so your emission, without learning, you do more at the start, and therefore it's optimal to strand more.
Frank, there's 3 minutes left.
Good. Last graph is the effect of uncertainty. So the effect of uncertainty is very small. That came a bit as a surprise to me, but then I started looking at other papers, and it's more or less a general outcome in climate cost benefit analysis. So we have here the blue line is what I've showed already, Epstein-Zinn relative risk aversion of 4. Now the red line is relative risk aversion of 1.35. That would then just be expected utility, much lower. And the emission paths, the optimal emission paths are very close. And so I think there are 2 reasons why these emissions paths are close. The one is that if you compare climate with having your money on the stock market, the uncertainty is quite lower. So we're talking about losing 2% of GDP, or maybe 3% of GDP, maybe 4% of GDP. This is a loss forever. This is quite dramatic, but in this model, it's two years of growth. So it's relatively modest. And then another thing, and that's a bit like that's work for future, that's future work. The model always, if there is new information coming on, the next year, the social planner will already adapt and set emissions optimally to the new information. So if there is an update of like the climate is more sensitive, the social planner adapts immediately. And so if you look at these temperature paths, they're in a very small range, although there is quite a bit of uncertainty going on. So that is not a feature of the real world. So the world policymakers would not adapt within a year to new information that comes in. And so that uncertainty is very much related to the fact that we are not on an optimal path. Anyway, so this is the outcome for optimal policies under uncertainty. Let me then conclude. We have several features typically absent in other models that flatten the carbon price path, meaning you do more efforts today and less in the future than in a simpler model, because we add inertia that flattens the carbon price path, cost benefit instead of cost effectiveness, and we have learning. So if you do cost benefit analysis and you start in 2020, then stranding costs are like the amount of repurposed capital is more or less 1% of total investment. That's reasonable, or I would say like modest. The total cost is 1.35 trillion. It's only in the first decade that you have these repurposing costs. If you wait until 2030, then things more than double, and the total cost goes to 4 trillion. And then if you do cost effectiveness, it's to stay within 1.5 degrees, then stranding becomes really a big issue. Even at starting in 2020, you're at 4 trillion. And something I didn't show, if you avoid stranding, if you do like your optimization, but you do not allow the model to go to repurpose capital, you lose quite a bit of value. So that would cost you also 5 trillion in welfare. So it's a bad idea. We should start repurposing as today and stranding some of the assets today. That is optimal. So I'm very happy to answer questions. This is the end of my talk.
Thank you very much, Frank. Do people have any questions? Let me start, and then maybe people start having their own. So I think that was a very interesting talk. I have a very basic question that regards the previous figures. Probably I missed something, and then more general questions that don't really have to do with your work, but rather with the message that you provide in your work. Can we see the previous slide, please, Frank?
Yeah.
So if I understand correctly, it means that not even in 2100, it's even difficult to pronounce that number, we won't achieve climate neutrality. Or is it we're not considering the...
So, yeah, how does that... so all these, the things that we generally see is that you have a lot of emissions today. It starts flat and then it goes to 2060 zero. That's so that is something that we also want to explore further. That is never optimal. So somehow, so there is one reason why IPCC reports have this. That is because they do cost minimization for at 2 degrees, a given target of temperature in 2100, but overshooting is allowed. You can go over this. And so that is a very ad hoc idea. It's not dynamically optimal. And therefore, you do a lot of, you postpone the effort and you go very negative after. So like many optimal of these scenarios, they wait more. Sometimes that is also like set by design. They think that before 2030, we can't do much. And then you would start later and then end with a lot of negative emissions. And so, yeah, that's... You're
basically saying that the path that we are committing to is suboptimal in a way.
Yeah. So definitely, like, these paths with negative emissions, I think that generally they are suboptimal. They have an arbitrage opportunity at the year 2100, at the end of the optimization period. They don't look after, or more technically, so they set a constraint that binds only from 2100. They allow for overshooting, and then you get this different path. And let me go back. So to start with, they do this. No, they do cost minimization. So they're on the red path, and this is approximation error. So you shouldn't think this is a true kink, but this is not a true kink. So it should go a bit better here. And so they don't go down that fast at the start, and because the climate sensitivity that I use is relatively large, and this total budget, so the area under the emissions curve is corresponds to what the IPCC says is the remaining carbon budget for to stay within 2 degrees. So yeah, so one of the things that is also not not necessarily optimized in these very detailed models. They don't have they have too much detail to do true cost minimization. So the learning is not always endogenized.
I think I have further question, but I think Xueting wanted to ask something. Am I right?
Yeah, I will be quick. Thank you, Frank, for this impressive work. My question seems a little dumb. Is the tipping point varies across countries, or I mean, if one country have some national incentives, like some subsidies to merchant the game? I mean, if the tipping points are the same for all of them, or it varies? Thank you.
Yeah. So this is a model that is like within the family of integrated assessment models. We assume that it's basically a model based on the representative agent. So whatever is dynamics between countries, it's not in. So it's just like what would be the optimal strategy if we want to maximize welfare in the world. And then it is true that a big disaster in one country, like if we model disasters as if they happen to the whole world together. So you can think of like methane would increase the world temperature. We all have the shock. We can't diversify the shock. And that's a bit different from the real world. If you have like the Indian monsoon changing, you can think of solidarity and the rest of the world helping India. That would like hedge some of the risk, but so in this model, whatever shock arrives cannot be hedged by solidarity between countries.
I think there's another question somewhere. Shahid, do you have
yeah. Okay.
Okay, please go ahead.
Yeah. Thanks, Frank, for your presentation. So I'm wondering on the assumption you made about the carbon intensity of capital, that the carbon emission, the carbon intensity has to be decreased by 5%. I'm confusing about this assumption because when you look at the capital over time, the efficiency rate might be falling. So I need a kind of a clarification. Why do you make such an assumption that the carbon intensity will be decreased by 5%? What do you mean by the capital? Is it the old capital? I'm not sure about that assumption.
Let me explain this better. So we assume that the carbon intensity is reduced without any climate policy by 1% per year. That is more or less the reduction in carbon intensity that is observed in the last decades in the world economy. So that's just like, since energy has a price, companies innovate and try to improve energy efficiency. That is 1% per year. But then this repurposing of capital starts at 5% of emission reduction per year, because if you just stop investing, and there the model has no costs for just stopping investing in fossil fuels, for example, or in coal-fired power plants, then the existing stock of capital gets older, decays, and like decreases in production by 4% per year. That's like a standard decay function in economic models. But often the decay is larger, but since we focus on these heavy assets, and if you look at the coal-fired assets in industrial plants, they have a long lifetime, around 50, and that is compatible with this 4% decay rate. So naturally, some plants arrive at end of life. They're going to be closed down anyway, and that allows you to abate at 0 stranding costs at 5% per year. That's the logic behind the model.
Okay, thank you.
Thank you so much, Frank. I think we now have to move to our next speaker, Larissa. So it's your turn. Thank you, Frank.
Thank you all.
So that was my presentation. I hope everyone can see it. Can you see my presentation?
Speaker, we get to see the speaker view. You have to use the mode.
You probably have 2 screens.
Yeah. Oh. Eigentlich, yeah. So. Sorry. Okay, yeah. So now.
Perfect.
Yes, now does it work?
Excellent. So the floor is yours, Larissa. Just as I did with Frank, I'll let you know when you have 3 minutes left.
Yeah, okay. So hello, everyone. Also a warm welcome from me to this session dealing with climate policy. My name is Larissa Fait. I'm research associate at the University of Kassel. And today I would like to give you some insights into our work investigating the costs of greenhouse gas emission reductions in the EU. And therefore I would like to start with a brief introduction into the topic and our motivation. So the European Union is very committed to global climate policy and aims to be a global leader in climate protection. And therefore, the EU is not only engaged to establish a global climate strategy, but also is constantly sharpening its own strategy and targets. And these efforts are also paying off. For example, the total greenhouse gas emissions of the EU were already reduced by 24% between 1919 and 2019, so that the 2020 target has already been early. However, future targets are far more ambitious and require more efforts to be reached. And for this purpose, the EU, as many other countries, mainly rely on the expansion of renewable energy generation and the investment in new environmentally friendly technologies and innovations. The main problem with these measures is that they are usually involve a lot of money and time. And so they are rather achievable in the long term than in the short and medium term. However, as we can see on the figure right, emissions need to be decreased significantly in the short and medium term in order to be able to achieve the 2030 target, but also the 2050 target. What is often underestimated and neglected in this whole discussion are issues of inefficiency, and therewith to what extent the removal of inefficiencies in the use of currently available technologies can contribute to achieving the current climate targets. Because such measures are also probably feasible in the short and medium term, and therefore might suitable for fast cut in emissions that is actually required. Of course, there are already studies investigating possible emission reductions related to inefficiencies in production activities. However, there are 2 main strands in the current literature. First, reduction potentials are often estimated at a very high aggregated level, as for example, at the country level, or even sometimes for groups of countries, such as developing versus developed countries. And in the second strand, reduction potentials are often estimated for a specific sector, such as transportation or agriculture, for example. Somewhat problematic about such studies is that heterogeneous industry structures of the compared countries are usually neglected when only the overall economy as such or only one sector is considered, resulting in a potentially over or underestimated reduction potential. For example, a country with a very large manufacturing sector can of course not be compared with a country that economy is mainly based on services. So accordingly, in order to estimate the true production potential of a country or group of countries, a differentiation should be made between the various industrial sectors. So our aim is to determine the total greenhouse gas reduction potential of the EU by differentiating between the different member states and several industry sectors in order to identify an optimal and cost-effective distribution of reduction targets between the countries and sectors. And to do this, we use a benchmarking approach to first estimate potential emission reductions as a result of inefficiencies, and in a second step, calculate the abatement costs of these potential reductions. Therefore, we basically compare the production performance of the countries in each sector using several input and output variables. So this also means we consider a relative inefficiency measure and reduction potentials. To do that, we need to determine the technology set, that is all possible input-output combinations. And secondly, we need to estimate the best practice function, also called the frontier function, which is determined by the efficient input-output combinations. So the frontier is the upper bound of the technology set, but I will show you that in a minute. To determine the technology set and the frontier function, we use the non-parametric data envelopment analysis that is commonly used for these types of studies. While the original DEA approach is a pure input-output analysis, the further development of the environmental DEA also allows to distinguish between the production of good or desirable outputs and bad or undesirable outputs, such as emissions, which can then be treated differently in the estimation process. And this is, of course, very important because the good output should generally be increased while the bad output should naturally be decreased. In addition, we apply a bootstrapping procedure to correct biased results and estimate confidence intervals for the reduction potentials. However, I do not want to go into detail about the mathematical programming of the DEA and the bootstrapping because they are very technical. Rather, I would like to illustrate briefly what we are considering. So, what we see here is the good output on the y-axis and the bad output on the x-axis. And for example, the points A to F are observed combinations of the good and bad output. So in this example, points A, C, D, E, and F determine the frontier because there are no combinations of good and bad output that are more efficient, meaning that there's no less bad output produced with the same amount of good output and vice versa. And according to the DEA framework, it is assumed that any combination between these efficient observations is also possible, so that the frontier is composed of these linear pieces. And all points below this frontier belong to the technology set T. So they are also possible, but they are inefficient, and so is point B. And simply put, our aim is to determine how observations like point B can be freed from their inefficiency and shifted to this frontier. And for this, we consider two cases. First, we could reduce its bed output and move horizontally towards the frontier. And this is what we call a pure emission reduction, and allows us to estimate reduction potentials while the good output is held constant. And alternatively, we could also increase its good output and be vertically shifted towards the frontier. This is what we call a pure output enhancement with emissions held constant. And for our analysis, we estimate these two models for each sector, because by doing this, we can compare the potential emission reductions with potential output enhancements. And this allows us to estimate the costs associated with the reduction in emissions. For our analysis, we have developed an own database that links production and emission data on the required sectoral level. And for this purpose, we use two existing data sources, namely the EU CLEMS database for the production data and Eurostat's air emission accounts for the emission data. From these sources, we concretely used 4 variables in our model, 2 input variables, namely labor and capital, and also 2 output variables. As good output, we consider gross value added in millions of euros converted with purchasing power parities in order to account for differences in national currency, and also to account for differences in purchasing power. And as the bad output, we consider total greenhouse gas emissions, which include all greenhouse gases listed in the Kyoto Protocol, and they are measured in 1,000 tons CO2 equivalents. Due to missing data for some countries and sectors, our sample consists of 16 European countries with full data coverage for 7 industrial sectors, namely agriculture, forestry and fishing, mining and quarrying, manufacturing, electricity, gas and water supply, construction, wholesale, retail and trade, and finally transportation and storage. And for our analysis, we consider a time period from 2012 to 2016, for which we calculated the median value. So one may argue that the scope of our analysis is limited due to the number of countries and sectors, but nevertheless, our sample is still representative for the EU, as 85% of the total greenhouse gas emissions of the period under considerations are covered. So this is mainly due to that all relevant countries and emission-intensive sectors are included in the sample. So now that I have explained our method and data, I would finally like to show you some of our results. Let's first take a brief look at the reduction potentials. Here you can see the absolute reduction potentials in 1,000 tons CO2 equivalents by country and sector. And first, across all sectors and countries, we have estimated an average total reduction potential of about 2.6 megatons CO2 equivalents, which corresponds to 77% of all greenhouse gas emissions considered. So accordingly, we find a significant reduction potential related to inefficiencies. And what we can also clearly see in the figure on the left is that the reduction potential is mainly driven by the emission-intensive sectors, namely agriculture, manufacturing, energy supply and transport, while the mining, construction and trade sectors only account for 7% of the total reduction potential. I do not want to go into detail here, but at the country level, we find that unsurprisingly, the large countries such as Germany, Spain or France also have high reduction potentials, while smaller countries rather tend to have smaller reduction potentials. Since the sectors A, C, D2E, and H mainly determine the total reduction potential, we have focused on these sectors when estimating abatement costs. And for this, we considered two different things. First, we calculated the abatement costs as foregone output enhancement. So therefore, we directly compared the potential emission reductions and increases in gross value added. So accordingly, here you can see the average potential emission reductions and output enhancement compared to the actual levels by sector. And what we can clearly see is that not only the reduction potentials are high, but also the potential enhancement and gross value added are high as well. We do find a positive ratio of potential reductions to potential enhancements for all sectors, but the emission reduction would be quite costly because the difference is not large for most of the sectors, so that on average, 72% reduction in emissions would cost about 60% foregone output enhancement, which is of course quite a lot. But we also find that this ratio is most favorable for the energy sector, which is quite interesting since the energy sector is also responsible for 40% of all greenhouse gas emissions, which would mean that a large proportion of emissions could be reduced at relatively low costs. However, here are average values considered, so of course there are national differences that have to be taken into account. Secondly, to get a better picture of the specific costs of reducing emission, we additionally calculated the marginal abatement costs for each sector. And again, we see that reducing emissions would be quite costly. Namely, on average, reducing 1 ton CO2 equivalent would cost about 860 euros. And I think this also indicates that current prices for CO2, for example, are far too low.
A clarifying question. So when you say marginal, do you mean per ton of CO2?
Yeah.
So it's above 2,000?
What? I didn't...
It's the figure above 2,000. So for instance, for manufacturing.
Yeah. Yeah, that's quite a lot, yeah. So yeah, for the manufacturing sector, these costs are very high, but it's only an average value. So we also estimated confidence intervals. And there we see that for some countries, these confidence intervals are very large. For some not, but for example, for Germany, the range is between 80,000 or 50,000 and 1,000. So I can go to this later. I can show these confidence intervals.
And all these numbers are about the social cost of carbon. So if abating costs us 10 times more than the social cost of carbon, I guess the conclusion is we should not abate.
Okay. Yeah, but if you look at the energy sector again, we find a rather interesting and I guess also realistic price, about 130 euros per ton CO2 equivalent, which indicates that there is indeed a large potential for reducing emissions due to inefficiencies in this sector, which could also be realized relatively cost effectively. For agriculture, we also find a moderate price of 375 euros per ton CO2 equivalent. Yeah, but for manufacturing and transportation, these costs are very high. But again, national differences have to be taken into account. So we can look on this if you want to later.
Larissa, sorry, you have 2 minutes left.
Yeah, this is, I wanted to go on with my conclusion. So overall, we find a huge reduction potential related to inefficiencies in the use of currently available technologies, and thus also a large potential contribution to achieving the current climate targets. However, the estimated potential enhancements and gross value added is also quite large, making the reduction of these emissions quite costly on average, and especially for the manufacturing and transportation sector. In contrast, emission reductions would be quite feasible in the energy sector, which is also the main driver of the overall reduction potential and total greenhouse gas emissions in the EU, so that here a significant contribution is identified. So that's my presentation. I thank you for your attention and look forward to your questions and comments.
Right on time. Thank you so much, Larissa. So I don't know if people have any further questions.
Hi.
Please
Hello.
go ahead.
Yeah.
Larissa, thank you for a nice presentation. So basically, you use the DEA, I believe is output-oriented distance function you use, if I'm right. Is it output-oriented?
Yeah.
Okay. So I want to refer you to your graph when you are trying to see how can the inefficient country or sector move to the frontier. There is another option there whereby you can increase your good output as well as increasing your bad output. If you are in point B and you move to point F, it means that you both increase your good and bad output. How do you account for that? Because there is a kind of debate on that where you use a directional distance function to adjust where you can maximize expansion of good output and maximize contraction of bad output. So how do you account for that? Then the second question is that there is debate on endogeneity issue. I'm not sure whether you account for the endogeneity problems, whereby there is a potential endogeneity issue with the input, since input is kept as a constant given the input. So how do you account for that? Then the third question is that do you account for the kind of a spillover effect among these countries and the sectors as well? Then the last question is just whether the path dependence, what you emit last year, could influence the emission this year. So how do you account for that in your model? Thank you.
Yeah, thank you for your questions. I hope I will remember every of it, but maybe I have to ask again. So the first question, generally our model allows to endogenously determine an optimal direction to the frontier. So this is exactly what you said, that point B also could be shifted to the frontier to C, to D, to E, to F, whatever. So the model also endogenously determine this optimal direction of increasing the good output and decreasing the bad output. But in our work, we did not consider this and estimated these direct directions, so a pure emission reduction and a pure output enhancement, because this is necessarily in order to calculate these abatement costs, so that you can say an abatement of this amount or reduction of this of the emissions would cost would cost the foregone enhancement of the output in this direction. And when we use these directions with an increase in good output and decrease in bad output, we cannot calculate the abatement cost as this. So, but we can do a lot with our data, and it is also our aim to estimate a model maybe with other pollutants. We also have data for CO2, for other air pollutants like NOx. So we will do this in another work, but not in this paper where we estimate the abatement costs. Your second question was regarding the inputs. They are of course considered in our model and to be held constant and are not to be increased or decreased. So they are assumed to be constant. Regarding these spillover effects, I think that was your third question.
Yeah.
I'm not sure whether we control for this. I have to think about it. Basically, we compare all of the countries in each sector and did not do a model for each country where we compare the sectors, because you cannot compare the manufacturing sector, for example, with the mining quarrying sector, because the manufacturing sector emits far more greenhouse gases than this mining and quarrying sector. So I have to think about it. I cannot answer at the moment whether we consider this. Unfortunately, your last question I didn't get. Maybe you can repeat it.
Yeah, it's almost the same. Whether what you emit last year also influence what you are going to emit this year, because like a path dependency, you have to put something, maybe what you have emission last year will also affect what you emit this year. Do you account for that path dependency? It doesn't matter, but just to know whether you account for that as well.
Unfortunately, our data is restricted to 2060 because there was this last update of the EU CAMS database. So we have data for the emissions, but not for the production data. But in another work within this project, we are also planning to make some projections to 2050. But this is only possible with higher aggregated data, because the sectoral data is often not available for a long period of time. So.
Okay, thank you.
Great. So if is there a further question? Frank, do you want to add something, or you just post it out on the chat?
Yeah, it was a question about like specifics for countries or companies. I was thinking about Norway. Like, are you confident that Norway isn't setting the efficient frontier in electricity? But that is because they have so many dams, and other countries they don't have the dams. So it looks as if they're doing very bad, but maybe they're at the efficient frontier, given the fact that they don't have dams. Or in steel, some countries, they have very small emissions, like less than half of the other countries in steel, because they remelt existing, so they produce from scrap. But there is not enough scrap for all countries to do all these productions. So is there enough specifics to, could it, like, how do you deal with this problem that maybe some specifics are absent and then overestimating the potential?
Yeah, that's a really good point. This is what I was also trying to make clear, that there are of course national differences between in these sectors, and that is also the point that of course a country with a large manufacturing sector cannot be compared with a country with a lot of services. And I think this is a part of the discussion to highlight with how feasible these reduction potentials are actually, how feasible they are in reality. And this is what we are currently doing to discuss, to look at these single numbers here. For example, you can see, of course, we have estimated these reduction potential for every country, for every sector. So in my presentation, I showed average value because these tables are often confusing and very big. And this is part of the discussion to account for these specific characteristics of certain countries and certain sectors, and to highlight how feasible these reduction potentials. And I think, therefore, it is also good that we have estimated these confidence intervals, where we clearly see that in some countries, of course, large differences are between the minimum and maximum reduction potential. But yes, of course, this is an important point of our work.
Great, thank you so much. So I think now it's time to go on to Xueting. So Xueting, the floor is yours. Thank you so much, Larissa, for this interesting.
Thank you for having me.
So can everyone see my slide and hear me clearly?
It's all perfect, thank you.
Okay. Good morning, afternoon, and evening, everyone. My name is Xueting Jiang. I'm a PhD student from Crawford School of Public Policy, the Australian National University. The other co-author of this work is Professor David Stern from ANU. The topic I'm going to talk about today is, did carbon emissions behave differently in the 2020 recession than in past recessions? The 2020 COVID-19 driven recession showed a sharp drop in carbon dioxide emissions as transportation and some other energy uses were curtailed. This was an unusual recession. Past recessions were primarily driven by changes in investment and central bank policies, etc., while this one was primarily driven by a pandemic. Thus, our research motivation is to know whether was the behavior of carbon emissions in this recession different to that in past recessions. If so, what does that teach us about the relationship between carbon emissions and economic activities? Some scholars discussed the asymmetric effects, like Sheldon analyzed an asymmetric response of emissions to falls and rises in GDP. In Sheldon's model, he distinguished a positive GDP dummy and negative GDP dummy by identifying whether GDP grows or declines using quarterly data. GDP is given in a given quarter was compared with that in the following one. For instance, a positive GDP dummy equals 1 when GDP grows and equals 0, otherwise in her model. We built on the literature on previous asymmetry studies. Besides looking into the difference when GDP grows and drops, we investigate whether asymmetric impacts exist between recessions and non-recession periods. With monthly data, it is possible to have some positive months of growth within a recession. This approach eliminates this noise. We include the interaction terms of recession, non-recession dummy, and the GDP growth rate. When a month is within an economic recession, the recession dummy equals 1. Otherwise, it equals 0. We use time series models estimated on monthly US GDP and the carbon emissions data to explore how emissions fall in recessions and rise in booms. We use the US economy as our research objective to investigate whether there is an asymmetric effect on the response of emissions to GDP changes. Monthly data are seasonal adjusted using the X13 ARIMA CEST program. The first difference of logarithm of carbon dioxide emissions and GDP are stationary after unit root test. Due to the data availability, we only identify the COVID-19 recession as February to December 2020. In this table, all the columns contain all data from January 1973 to December 2020, while even columns include data ends in December 2019. This setup is to compare the response of carbon emissions with and without the year 2020. Results in Table 1 make us wonder why the asymmetry on carbon emission elasticity of income becomes statistically significant after including the COVID-19 recession. How the 2020 recession breaks previous insignificance of the aggregated impacts. Is the 2020 recession different with past recessions in affecting the response of carbon emissions? One possibility is during previous decades before 2020, there is offsetting effect. Specifically, for some periods, the emission elasticities of income are significantly positive, while impacts for the rest years are not statistically significant. Then the integrated impacts could be insignificant. And one potential reason why the 2020 recession breaks this insignificance of previous emission income elasticity is the unprecedented collapse in global economy. This may have altered the relationship between carbon emissions and GDP with cumulative impacts. Therefore, it is necessary to further compare the 2020 recession with past recessions individually to further figure out the mechanism of each recession. Sources of past recession before 2020 differ. Some were primarily associated with oil supply shocks, while others were mainly associated with banking policy adjustment or financial market turbulence. Could these factors affect the response of carbon dioxide emissions to GDP growth? This question is crucial, but not well documented in previous studies. According to the definition of NBER, a recession is a period between peak and trough of a business cycle, and expansion is a period when the economy is not in a recession. Expansion is a normal state of the economy. Between 1973 and 2020, 7 recessions are identified. This table shows the start and ending time of each recession. Thus, we want to compare across recessions individually and see whether the asymmetric effect vary across economic crises. The coefficient of the interaction term between GDP growth and the recession identification term captures the asymmetric effect during each recession. This method provides us a way to compare individual recession and review the differences. These are some results. Apart from the year 2020, during 1973 to 1975, 1980, 1990 recession, asymmetric effects on emission income elasticity are significant. This makes us interested because these 3 recessions are also associated with 3 oil supply shocks in the US history. For example, Organization of the Petroleum Exporting Countries placed the crude oil embargo against the US in 1973. The consequence was immediate and effective. Due to the supply shock, first oil crisis erupted and brought about the recession. The asymmetric effect on emission elasticity of GDP growth is also found significantly during the COVID-19 recession, but unlike past oil crises, oil shocks during 2020 recession is mostly associated with a negative demand shock. For the rest of recessions, where not significant elasticity is seen, the financial crises are primarily affected by central bank policies, investment, etc. For instance, the Great Recession lasts from December 2007 to June 2009, is normally considered to be related to subprime mortgage crisis, and the early 2000s crisis is relevant to the stock market bubble and the 9/11 terrorist attack. Therefore, it makes sense to make the hypothesis that sources of recessions are important in affecting the response of carbon dioxide emissions to GDP. If a recession is associated with oil crisis, it is likely a symmetric effect exists on carbon emissions compared to expansions. However, recessions related to other financial or monetary factors, no significant asymmetric effects could be detected. Recessions associated with negative oil demand or supply shocks may affect asymmetry on emissions between recessions and expansions. To further check this hypothesis, we then regress with emissions only from oil and compare with the regression results from total emissions. When regressing carbon emissions only from oil consumption, a symmetric effect during recessions are larger than using total energy-related emissions. Table 5 shows the result when we comparing across individual recessions. Column 1, we use total emissions as response variable, and column 2, we use oil emissions as response variable. In most recessions, the coefficients become larger for identified recessions with significant asymmetry. Then we regress petroleum consumption and other energy uses on GDP growth by saying other energy uses are referred to coal and natural gas consumption. We mainly focus on fossil fuels. The residuals represent excess oil or other energy consumption. Figure 2 shows excess oil consumption. The horizontal line represents 0. Negative values below this line means in this month, huge drop occurs for oil use, and the drop is greater than the average level. For some recessions, the positive values and negative values can almost offset each other. However, for some recessions like 1973 to 1975 and 1980, negative values have more proportion. Some people might argue that total energy use, Some people might argue that total energy use also decline during recessions. To eliminate this noise, we also compare the excess oil use with other energy use. So figure 3 shows excess coal and gas in each recession. For the more negative recessions we mentioned in last slide, no significant asymmetric effect are shown. Changes above and below the horizontal line did not vary a lot. To investigate what primarily drives the asymmetric effect, we then decompose carbon emissions into energy use and the emission intensity of energy use. Decomposing emissions reveals through which channel the emission income elasticity is affected. The monthly emission income elasticity is separated into two portions, energy use and carbon intensity of energy use. The elasticity of emission intensity of energy with respect to GDP is 0.35, while the coefficient for energy use is 0.64. This indicates more emission changes relevant to energy use compared with emission intensity of energy use with same GDP changes, but some are still related to emission intensity of energy use. These changes.
Do you about this figure? Do you hear me?
Yeah, I can hear you now.
These estimates of the elasticities, I find it's very interesting. Does it relate to the whole sample or just the last crisis? I guess these numbers must have changed a lot across time as well as across countries, depending on the energy intensity of the sectors they rely on.
We only use the US economy as our research objective. So the data is based on the US data. We didn't consider other countries. So maybe we could do other countries in next paper or something like that. Yeah.
This relates to the last crisis or to the whole sample?
I'm sorry?
These figures relate to the last crisis or to the whole sample?
It's whole sample. Yeah.
And you haven't analyzed whether these elasticities have moved over time? You don't?
It contains all the time periods that from 1973 to 2020. So it includes all the data. Yeah. Is that good? Thank you. And this change related to emission intensity of energy use could come from mitigation methods like fuel switching. We also compare across sectors to investigate in which sector emissions are more elastic to economic loss during recessions and how large is the asymmetry. Transportation, commercial, industrial, and electric power sectors had significant asymmetric impact on emissions during recessions. If looking into energy use, GDP asymmetry, primary energy use is more elastic to GDP growth in transportation sector. In other words, the asymmetric impact on emissions in transportation sector during recessions is more relevant to the channel of energy use changes. This also in line with why the 2020 recession could make the asymmetric impacts stand out by greatly affected the transportation sector. We reached some key conclusions. Sources of recessions are important in affecting the response of carbon dioxide emissions to GDP. If a recession is associated with oil crisis, it is likely a symmetric effect exists on carbon emissions compared to non-recession periods. However, recessions related to other financial or monetary factors like banking policies, etc., significant asymmetric effects could not be detected. Significant asymmetry effect compared to booms during 1973 to 1975, 1980, 1990, and 2020 recessions are detected compared to booms. The 2020 recession is mostly associated with a negative oil demand shock, while past three recessions that had significant asymmetry are associated with crude oil supply shock. These are some key references for slide. Thank you for listening, and any comments are welcome.
Thank you so much, Xueting, and you didn't even do it during less time than allocated, so we now have more time for questions. So does anybody have any question for Xueting?
Xueting?
Yeah.
Thank you for a nice presentation. So the first, like a comment or suggestion, do you think about whether to the elasticity, whether you consider the short-run elasticity and long-run elasticity? You consider that in terms of breaking the elasticity into short-run or long-run elasticity? Do you consider that in your paper?
Yeah, sorry, we didn't include the long-term elasticity. We only consider the short-term one, but we could include the long-term one to make comparisons. Thank you for the comment.
Then the second is that I'm looking at the, when you're dealing with its time series, there is a lot of procedures someone needs to take in order to specify or transform the variables. So like conducting the stationarity unit root test or see whether there is a kind of a co-integration and some other approach. Do you take those approach before you move to your specification of the model?
Yes,
so
thank you
like
for the call.
Whether there is like a co-integration, then the speed of adjustment and some other, since the pattern of the time series analysis. And then do you conduct any robustness check in terms of your residuals, and some other stability of the functional form and some other things, the functional form of the model, the specification of the model and all the stuff after you finish the estimation, because this make your estimate to be more robust and not to be biased. That's what I'm just thinking about. Do you consider all those steps?
Yes. Thank you for the useful comment. That's I can tell you what I've done. We have checked the
yeah. Just make it brief because it's like what you have
I think you are.
Just make it brief. Yeah. Can you hear me?
Yeah.
Okay. Continue.
Yeah, I think I get your point. I think you are totally right. I'm absolutely agree. I have done to check the stationary of the time series. So we did a logarithm and the first difference. We didn't add any lecture or something you said that, but we plan to do that in the later course. Currently, we are more interested in to interpret the association between carbon emissions and the GDP changes, and not the causal relationship. But we will do it in our future, like adding more leg terms. That's quite useful. Thank you.
Okay. Do you see any robustness check after you do your estimation to see whether what the estimation past some of those methods you have used so far?
Yeah, I had done some, but I didn't add it in my slide.
Okay. Thank you.
Thank you.
Hello, can I ask you a question?
Yes, please.
So I mean, Yifan and it's a wonderful presentation. I like it, and I may have few questions. And the first is like the oil crisis. They come from the different reasons. Some are from the war, some are from the pandemic, and some maybe from the demand or supply. I think maybe you wanted to divide all the crises into two sides. And the first is the crisis from the demand, and another is the crisis from the supply. I think the last year when we have the COVID-19 pandemic, the crisis is from the supply side. We have too much supply, and you're using the data from the United States, and they probably have lots of the supply. It's really expensive to close all the wells, all the factories, all the oil fields in the one time. So the price of the oil dropped sharply. For the Texas oil, they dropped sharply. So you may want to to track the original reason of why the crisis is happening and separate that into different groups. This is the first, and then second is like the emission, the oil price. The oil price is the energy price. It's something you have to spend to make your production. And all the departments, they're doing, they make some output, and some of them, they're depending on the oil, some of them, they are not. And some of the emissions, they have come from the production, some are not. So you may want to think about the department, why they come from, where the carbon emissions came from. And I may have a question on table 3, but no, never mind. And the oil energy price is, it's a big thing you want to take into consideration, because in the different crises, the oil price is different. They varies a lot. Some of them, they even reach the negative, and some of them, they reach very high compared to the previous time. And the fourth and my last question, comments, maybe, you're using the data from the American, but American price and demand is it was impacted by the whole world. Probably you can use regional data. I know American, they have tons of data from the IAEE. You can use from the different states, and the emission, they have a different state level, and the oil price, they have oil price, they have different from the different states, and the GDP, they also have a different state from the different states. So you can maybe do all your stuff in the one time. I mean, you use your same model and use the same period, but just use whatever 50 or 51 state in America and do it again, and to see what happens, what the result will be. Thank you.
Thank you. Yeah, it's quite a lot helpful comments, which made me think a lot. So just one thing I want to clarify. So we are not using oil prices as our control variables. Maybe we can control it as a control variable, I mean, in the future. But mostly we are using the oil consumption for now. And the thing you mentioned, yes, the regional difference, yes, it could be useful. And we add some sectoral comparison. But sorry, if you said a department, if you mean sectors or?
Yeah, different sectors. It's not,
yeah.
It doesn't mean it's the transportation, just one part, and you can go to the cinema, and maybe the Disney park, whatever they come from, they have different impact. And the comeback, the coming back, of the demand is because, I don't know why, maybe of the national days, it's because of the holiday. It's because of temperature changing. It's like that's the thing you have to take into consideration, because you have the I don't know, monthly data or quarterly data you have, and you can control the temperature, why the consumption varies in the period. Yep.
Yes, temperature could be. We will test that, but I thought we have done some seasonal adjustment. We can control that for some degree, but we will check the temperature, whether temperature will affect the result. Thank you. Yeah.
So any other questions? Frank, you had a comment. Do you want to just leave it on the chat, or?
I'll leave it on the chat. So Xueting, it's an idea. So maybe it's useful.
Okay. So if there's no further issues, I'm just want to thank you for your work, for your time, for your presentations, and wish you all the best with the prospects of your research. Thank you.
Thank you.
Thank you.
Bye. Have a nice end of the conference.
Bye.